So we have been discussing over the time like how the memory is being managed. Now then we discussed about that there are two views of memory addresses which are available. One is logical addressing, another is a physical addressing space. So there are two addressing spaces existing. Your CPU is generating logical addresses. So those are split into pages. And from the pages, once we got the page number, we try to map that to the physical memory address. That mapping is performed by page table. So for the page table is per process data structure. Remember this, this is per process data structure. So we discussed about inverted tables. That was a global table. And the page table is per process. So each process would have this page table, which contains the information about the pages it needed and their mapping into the physical memory space. Then we discussed about how the trap is generated and how this magic is done. What is demand paging? So demand paging is whenever it is requiring a particular page, whenever a process requires a particular page, only then it is called from the back storage or from the secondary storage and put into the main memory, and then the process is actually initialized. So for that, our valid invalid bit is very successful and help us to do the task. So whenever that the bit for page table is invalid I, so then if there is a request from CPU for that particular page, then it will generate a trap and bring the page back to the RAM. So we also discussed about that there are problems with it, and we discussed about okay, so we were here. So what happened if there is no page, no free frame available? Like we discussed in the previous lecture that if we increase, we do the demand paging and just bring those pages which are required into the main memory, that would increase multi-programming. Now there should be a max limit till when, till what amount we can multi-program our system. So if we allocate all the frames in the memory, because there would be fixed frame available in the memory. So then in that case, a process wants to fetch another new data into the RAM, then already we have no free frame available because all of the memory is already allocated to n number of different processes. Let us suppose the example I was taking, let us suppose we have 40 frames, and out of these 40 frames, we wanted to run four processes, each with 10 pages. So each one is having 10 pages requirement. So we can easily fit the full process into the RAM because each required 10 pages. So 10, 10, 10 we can do. So multi-programming is index is, let us suppose, 4. So in this case, we can increase the multi-programming if we run process P1 with half of the pages only. So let us suppose we do this. P1 is running with P5, P2 is running with 5, P3 is running with 5, P4 is running with 5. Now with this, we have only 20 frames consumed from the memory. Now there are 20 which are free. So what we can do, we can add more processes, and let us suppose there is P5 with 5 pages, P6, P7 and P8. So all are given, 5, 5, 5. So we allocated all 40 frames. Each is given 5 frames. Now we have allotted whole of the RAM to different processes. So our multi-programming factor increased by 8. But what happened with this? Whenever a process, because P1 is running with 5 process pages, it would require, or it may require, 6 pages or the rest of the 5 pages. It may ask for to bring in, a trap would be generated and ask, this process is running and asks for the next 5 pages. In that case, what would happen? Because your RAM is already allocated. Now there is no free frame available, but your process P1 wants to fetch more frames and there is no space for it. So we discussed about this question mark. If there is no space, then how we would be allocating this frame to from into the main memory, and how this process P1 would actually get executed, because it requires that page and it's still not into the main memory. Then how this would happen? So here we say we use a page replacement algorithm. That's what we are going to discuss. So there are two things that we are going to discuss today, is page replacement and frame allocation. So for page replacement, there are algorithms, uh, and why do we need it? Because we want to execute the process. If there is no page frame available in the main memory, then one option we can terminate the process, but that's not a good way of doing. Another way is the swapping page with page replacement. So what we can do is, so whenever there is a request and no page frame is available, what we can do is we can put any victim page to put back into the main memory, and this would get freed and this would be sent here. So with the paging with the swapping would make this possible for us to select the victim and then put it back onto the secondary storage if it is not used, and that free frame is allocated to the new frame. So this is how we are going to implement. Now the condition, the question is, how do we find out the victim? Which victim you should be which victim should be replaced and swapped back to the main memory? So those algorithms we are going to discuss today. Now, is the problem clear to everyone? What we are going to discuss? Is it clear till now? What I went over? Okay, great. Thank you. So the basic page replacement is, if there is no free frame, and we find that that is not currently free yet. So we basically try to find out the victim frame. We can free a frame by writing its content to the swap space and changing the page table to indicate that the page is no longer in the main memory. Now we can use the free frame to hold the page for which the process the page faulted occurred. And in that case, our algorithm, which we discussed in the previous lecture, would be modified. Find the location of the desired page onto the disk. Find the free frame. If the free frame is available, use it. If there is no free frame, then use page replacement algorithm to select the victim frame. Write the victim frame to the disk, and bring the desired page into the newly free frame, update the page table frame, and continue the process by restarting the instruction that caused the trap. So these are some steps which would be followed when we are using page replacement algorithm. So this we discussed in the previous lecture also. So I'm just making it double clear, like how that would happen. So if there is an invalid, it will generate a trap. Trap would try to find out the free. Now it selects which frame is to be replaced. Then it will select, is there any free frame available? Then an algorithm would be acted, find out the victim, and once it is found, it is swapped out, and the new page, the desired page, is swapped in. And after this is done, this entry would be created as an valid, and the whole of the process instruction would start. Now, in addition to it, whatever what we were discussing, to reduce the overhead. Now, what is happening? You can see that what we are doing here is we are swapping out and then we are swapping in. So we perform the swap out and swap in. Now, let us suppose this is a frame which includes some variables. Let's see the count variable. Okay, so it is stored in this victim frame. If the value of this count variable is not modified, then the page in the main memory and the page in the secondary memory would be same. So the value of count here and here would be same. Do you agree on it? Okay. So is everyone up to the same page, like what I said? Or okay, that's good. So what I said is if there is no modification in the account, nothing has been modified into this frame because actual modification is done in the main memory. So CPU writes back to the main memory. If this victim page is not modified, then this victim page and the page which is residing onto the secondary memory for this would be same. Okay. So in that case, we need not to perform this swap out process. Only we can copy this from here to here. So what would be the effect of this? We would reduce the swapping. IO would be reduced for us because otherwise what we are doing is we are swapping out and then swapping it. So there are two steps. But if we can identify whether this frame is updated or not, we can reduce this swap out process. If it is not modified, whatever here is same here. If uh, it is modified, this is different than what is here. So if it is not modified, both are same. So if not modified, we can skip this step. So that's what is modify bit. To reduce this overhead, modify bit is added for each page or the frame. There is a modified which is associated and taken care by hardware. So some bits are flags are hardware generated, and this is basically managed by hardware. So hardware would set the modify bit if the contents of the page has been modified. And now if we want to run the algorithm, if the algorithm is running, try to find out the victim frame, can look into the modify bit. If the modify bit is not set, it means that there is no change has been done and there is no need of swapping then. So that would actually reduce our process. If the victim has been identified and changed, then we have to perform the swap out. So with demand paging, the size of logical address is not constrained with the physical memory. This we have already discussed. So what is needed, two things. One is a frame allocation algorithm, how many frames to be allocated to one process, and then is a page replacement algorithm. So each frame allocation algorithm we will discuss after page replacement algorithm. So page replacement algorithm wants to know about the victim. So who is the victim frame? So which one is a victim and we have to remove. So what's the lowest page fault rate on both first and reassess? So to evaluate it, we have a reference string. So this reference string to evaluate different algorithms, we are going to use this reference string. So what it is this is basically the page number. So the request is for 7 page, 0 page, 1, 2, 0, 3, 0, 4, 2, 3, 0, 0, so on. So these are entries. So here we are using this reference string to compare different algorithms for page replacement. Okay, so the first algorithm that is, we have discussed this algorithm and familiar with this particular thing. So it's a key. So whatever first in then goes first out. So we are going to use this reference string to evaluate the number of page faults. So how many page faults would be there? And we are going to consider that there are 3 frames in the main memory. So only 3 frames are available in the main memory, and we can keep three pages in the main memory at one time. So let's consider and draw this. What would happen initially? Initially, there's nothing in the main memory. So the call to this 7 would create one page fault because there is nothing in the main memory. So the first page would be called 7. So there will be one page fault. Agree on it? Is it clear? Yes or no? Or yes, this is a page replacement algorithm here. We are going to talk about that. So first in, first out. How it works, I'm explaining it right. So are you agree that whenever there is nothing, so this is your RAM, and when there is nothing in the RAM, no frame is occupied, so a request to the first frame, so your CPU would generate this page fault. This page fault would go into the page table, would look into, okay, this is I, then there is a page fault. The trap would be initiated. Once the trap is initiated, it go to the secondary memory, take out the block, put it into the frame, because all the frame, we say any frame can be allocated. So let us suppose I allocate this to 7. So page number 7 is now loaded. This does not mean the content are 7. This is just a representation of a page number. Now contents would be different. This is just a label. So here it is a label. So page number 7 is loaded into. Now the next request by CPU is to the logical address space, page 0. Okay. In that case, again, page table would be looked into. The I for that page table, this is your page table. So the first, let us suppose this goes like 7, 2, 3, 4, 5, 6, 7. Let us suppose like this. Okay, now initially for every one, it is I. Now the first, when CPU gives for this, I is invalid. It means that a trap is to be generated. So trap would be generated. So once trap is generated, it will do the process, whole complete process to fetch it and then update it back. So now this would become V. Okay. So 7 for page number 7, it will become V. And now the next turn is of page number 0. So CPU generates page number request for page number 0. The page table entry for this process would be looked into. It is again I. Now in that case, a new trap would be generated. So if this is a trap, the whole process complete cycle would be done to fetch the frame from the secondary storage, update back, put it into the RAM, and update this page entry, so that this would become I. This would become V after the fetch process is done. Now the next request is for 1. So 1. So again, this is I. Again, this is a page fault. So again, this would create a trap. Now for first 3, 7, 0, 1, how many traps are there? How many page faults are there? Any answer? How many do you think there are? How many traps are there, or how many page faults are there? 1, 2. Because your RAM was empty, or not. I'm not asking for the complete. I'm just asking for this much. So till here, there are 3 page faults. How? 7 was not into the main memory, so there was a trap. So whenever there is a trap, we say it is a page fault. Then the second trap is for page number 0, and third trap is for page number. Am I clear on it? So till here we have 3 page faults. Now there is fourth is 2. So it is making a request to CPU, making a request to page number 2. And in that case, what would happen? Now you can see your RAM is full already, 701. So 701 is already allocated. All the frames are busy. There is no free frame. Now there is a new request for page number 2. The algorithm is to be used to do the page replacement. Okay. Now which would be the victim? This algorithm is stating the first in, first out. So the first frame that is entered into this particular queue, that would be the one which would go out. So you can see this is in the queue. So 7 is the victim that would go out and make a space for 2. So that's why whenever a page fault 2 would happen, so 7 would go away and it would be replaced with page number 2. Is this clear? because this is a base of everything, whatever we are going to do. Please, any yes or no? Okay, is there anybody who wants to repeat this? Okay, I think everyone got it. So whenever there is a request for two, now we can see that the first page which was added to the queue was 7. So 7 would be replaced now. Now here, the next call by the CPU is to 0. So you can see this is a valid page. It's already in the memory, so there is no page fault. So till here, how many page faults are there? So there is 1, 2, 3, and 4. So there are 4 page faults. Till this 0, there are 4 page faults. Number 1 page fault, number 2, number 3, and number 4. And for 0, there is no page fault because 0 is already inside your memory. Okay, now moving forward. Next call is 2. So now it's 3. 3 frame number 3. This is frame number 3. This is invalid. Now this is invalid. So now we have valid is for this 2, 1, and 0. So 2, 1, and 0 are valid. 7 is out. So this is invalid. Now this is the state of our page table when the request of 3 is coming. Now we can see again the same situation is there. There is a request to page number 3. Its bit is I. So there is a trap, means the page fault. Whenever the algorithm would work, come back, it will see that our queue is already full. So it's like this. So already RAM is full. Which would be the victim to replace? It would be first in, first out. In this case, it will go like this. Now the first at the top is 0. So our RAM would be now holding the 0 would be replaced by 3, and there is a page fault. Now this is another page fault. Page fault number 2, 4, and 5. And now there is a call to page 0. We just replaced it. So it would create another page fault. As I was discussing, that if the frame is not in the main memory, it is not an error situation. It is a situation that we need to fetch the data from the memory. So that's the only problem. Otherwise, there is no problem in keeping our data onto secondary memory. So what would happen? 0 would create another page fault. And what would be replaced? 1 would be replaced because it's a first in, first out. Okay, so we keep on editing this and we keep on replacing. Then 4 would be replaced by 2. Then 2 would be replaced by 3. Then 3 would be replaced, 0 would be replaced by 3. And then 0 would be replaced by 4 because of, then we have a calls to 3, 2. So 3, 2 are already there. There are no page faults here. So 7, 8, 9, 10, 11, 12, 13, 14, and 15. So using first in, first out algorithm, we have 15 page faults. So this is one algorithm of we're doing. So, okay, moving further, there is a problem with the first in, first out. We can think of how we can reduce the page faults if we have more memory, more RAM. You can keep more number of frames into the main memory, then there would be fewer page faults. We remember we discussed about the performance degradation in the last lecture, like how many page faults should be there. So we were thinking of, like, if we keep on increasing the RAM, there would be fewer page faults, but there are certain algorithms those suffers with B-Lady anomaly. So B-Lady anomaly is, even if we increase the number of frames available, there may be the number of page faults may increase even then. So here is a test which is performed, and they say that the first in, first out algorithm suffers from B-Lady anomaly, that even if we keep on increasing the number of frame, the page fault may increase. So here you can see we have number of available frame 3. The page fault number is something around 9. And if we make the page number of frames 4, and at that time the page fault number become 10, so it basically deteriorates the system. So this gap peak, this difference is called whenever there is an increase in page fault number while increasing the RAM, this situation is called, this problem is called P-Lady anomaly. Am I clear on this? Okay, thank you. Now, coming to optimal algorithm. What is optimal algorithm? How it works? The concept here is identify the victim page that will not be used for longest period of time. So we don't replace uh, we don't replace a page that will not be used for longest period time. So we replace a page that is not going to being used in near future. So I'm giving and victimizing those frames which I see, okay, I don't need it. So how do I know this thing in the future? Like what frame would be called next? Now this is an hypothetical situation, like I cannot predict it. So something similar, remember we discussed in shortest job first. So we are not sure about which job would be the next one, so we make few assumptions. So similarly, the optimal algorithm is not actually realized algorithm, but this is an algorithm which gives us the optimal solution, and it will give the optimal number of page faults. This is used as a benchmark to compare with other algorithms. So optimal algorithm looks into the future to find which frame should be removed. Initially, now let's think about the same state. So RAM is empty, your RAM is empty. So 7 would create 1 page fault, 2 page fault, 3 page fault. Till here, it is same. So 1, 2, and 3 page faults. And then when we are going to replace 2, now this 2 would be replacing a frame which would not be used for longest time. Now we have to see which one is not being used for longest time. I start with 0. 0 is used just next to this frame. I say 1. 1 is used here. And what about 7? 7 is being used here. So which one is not being used for longest time? Any answers? Which one do you think is not going to use? The answer is already there. So it is just your understanding that you understood it. It is going to be the 7, because 7 is going to be used much after the other frames in the queue or in the memory. So we are prioritizing based on the longest period time use of the frame. So 0 is just being used next to this frame, then comes the 1, and then the longest period here on this based on this queue is your 7. So 7 is the one which is a victim here. So we replace 2, and then it will become 201. So now next call is for 0. 0 is already there. So there is no page fault. So page fault number 4. And then there is a call to 3. Now 3 would be replacing which one out of 201? Which one should be replacing it? Can anybody tell me? Let's hide it. So which one should be the next? Okay, 1. Why? Because 0 is being used next, 2 is being used here, and 1 is being used here. Now, so here your victim is, so what we are going to do is, we are going to replace 1 with 3. So this is done. Now next is 0, so no page fault. We have 5 here. Then we have 4. Then we have 4. So now page 4. Would there be any page fault? Yes. So which one is the victim next for this? Shao, can you come up with your question, because it won't be used for 10 frames? Which one? 1? I did not get your. So which one is the victim for this? 2, 0, 3. So what, we are here. We are here. So we are here. And here we have to make a judgment. Frame should be replaced. So there is a page fault for 4. There's no memory space available. Now, which one would be the victim? I see in the future. So I see 2 is used next. So 0 is used after this. And then 3 is already used here. So 0 is being used. So which one is used after a longest period of time? It's 0 here. And we would be replacing, 0. So 4 would be coming in place of 0. So that's why it is here. Now 2 already there, 3 already there. So no page faults. Now we have 0. So when it is 0, which one would be replaced? We again we look from here. We are standing here. We look into the future. We look into the future. Which one would be used after, longest time? So 0, I'll look here. 2, 3 is used just after it. 2 is used just after that. And 4, where is 4? There's no call to 4. So what I can do is I can replace 4 with 0. So now this is page fault. And then we have 1. So again, I do the same thing, 8 and 9. So our optimal algorithm generated 9 page faults. So is it clear to everyone? Thank you. Okay, now you have to tell me the page faults. Okay, now there is another algorithm because your optimal algorithm does not exist in. Oh, there is a question. Is Zian 9 means page number? No, 9 means the number of page faults for this sequence, for whole of this sequence. So the sequence was 7, 0, 1, 2, 0, 3, 0. What are these? These are the page number requests from CPU. Whenever there is a page number request and we have only 3 frames in RAM, okay? So whenever there is a page request, if the page is in the memory, then there is no page fault. If the page is not available in the memory, then there is a page fault. Agree on it? So what we calculated here is the number of page faults. So with this sequence, whenever this is a call, with this sequence, what we have discussed with this sequence, this is a call. Okay, so this is how our CPU is going to call the pages. So based on this, we want to see how many page faults would be there. How many page faults would be there based on this algorithm, the algorithms we are discussing. Zian, did I answer your question? Anyways, I'm not getting a response. Okay, so the optimal algorithm does not exist in actual practice. So what we do is we use least recently used algorithm. As the name says, what we are doing here, we are looking into the past. So rather than looking into the future, we are looking back towards the past. So least recently used frame would be the one which would be the victim. Is it clear to everyone? So now this is similar. So we are, rather than making forward, we are just looking back. So let's start this. Now this is the sequence by which our CPU would be asking for the page numbers. Okay, so these are the page numbers, and based on these we have only 3 spaces in our RAM, and now there would be page faults because we cannot accommodate all the frames into the RAM because of 3 frames only. So there would be a number of page faults those would happen, and let's see how that which algorithm creates a minimum page fault number. So the sequence first, so RAM is empty. When 7 is called by CPU. This is not into the memory. How? Just to making Xiang clear. So whenever there is a call to 7 page number 0, 1, so on 7, the bit for all are invalid. So page CPU would call this page number. So from this page number, we look into I. This is invalid. Then it creates a trap. So that trap is doing, this trap is going back to the secondary storage, identify the frame which is to be replaced, find the victim and replace this, and come back and update this page table. Okay, so once the trap is done, your 7 would be fetched into RAM, because everything in the RAM is free, because this is the first frame we are fetching. So there is no problem of page replacement, but there is a page fault. So page fault is there. Okay, so page fault number 1. When 0 is called, because it is not into the main memory, so page fault number 2. So same for 1, page fault number 3. Now what would happen for 2? For 2, so we have to look at which one is the least recently used. So replace a page that has not been used the most amount of time, so which is not being used just now. So we have to find out that particular frame. Okay, so 777 has not been used in most amount of time, so it is not most recently used, so let's remove it. So this becomes a victim. So this is basically is an algorithm that use the activity of using recency. Okay, so then 7 is the one which is not recently used, then it will become the victim here. So what we do is we replace it, but there is a page fault here. So one is a page fault, another is page replacement algorithm. So 2 would be replaced. Now next call is 0. 0 is already there, so there is no page fault. Next call is 3. Now, can we answer which frame would be replaced next? So everyone is saying 0 is recently used, and 2 was used, and then 1. So everyone is saying, so 1 is replaced by, yeah, go ahead, answer it. If you answer it, this is clear, all clear. You need not to read this algorithm again. Can I see more answers? Anyone? There are 34 participants. Okay, so this is 203. So 3 is replaced. Now, next call is for 0. Okay, so 0 is already there. So there's no page fault. Here's page number fault number 5. Then next call is for the frame 4. Now 4. Which one would be replaced now? So yes, Eric. Yeah, you are correct. Let's see. Here it is. So 2 would be replaced by 4, and now there is another call. This is another page fault. This is another call. Which would be replaced? 3 would be replaced because not recently used. 4 just came in, 0 just used, and so it will be 3. And for 3, which one would be replaced? Okay, let's see. And now there is a call to 3. So what do you think? Which one would be replaced? There is a call to 0. Which one out of 4? 4, very good. And now the call is to 3. So 3 is already there, 2 is already there. Now there's a call for 1. Here, I'm at this point. So 1 is being called by CPU. Already in the memory is 0, 3, 2. Which one would be replaced? 0. Okay, now 2 is already there, 0 is the next call. So 3. Now 1 is already there, 7 is the next call. Which one? So 2. So this is how we go, and these are the number of page faults that are created. So it is better than first in, first out, but worse than the optimal. So that's why optimal is always used as a benchmark algorithm to identify, to find out which algorithm is the best one. So there are different methods to implement it, but this is not that important. But yes, these algorithms, least recently used as well as the optimal algorithm, they do not suffer from B-Ladies anomaly. They do not suffer from this B-Ladies anomaly. And these are class of algorithms called stack algorithm. So a stack algorithm is an algorithm for which we can show that the set of pages in the memory for n frame is always subset of the set of pages that would be in memory with n1 plus 1 frame. So if we increase the number of pages, then that would be the subset. So this is kept This is definition, but the stack algorithms are the one which are not suffered with B-Lady anomaly. So B-Lady's anomaly, as we increase the frame, so there should not be increase in the page fault number. It should actually reduce. Okay, so least recently used, they need special hardware. So that's the problem. They need special assistance to get a work and represent. Now they are still slow. So what can be done? What is an alternative if you don't have a very good hardware available? You want to reduce the cost of your computer system. What could be the other alternative? Then it is added a reference bit. What is a reference bit? Many systems provide some help in the form of reference bit. With the page, associate a bit initially 0. When the page is referenced, this is set. So we discussed about the modified bit and now the reference bit. Modified bit is the one which used to look into whether the page content is modified or not. The reference bit is the one which is used to see whether the page is referenced or not. We have put that into the frame. Okay, so we have put that into the main memory, whether it is being called or not, it did get a turn or not, because we have discussed only about a few frames. We were just bringing one by one. If our memory size is large, then we will allocate the frames in bunch to one process. Let us suppose I say I give this each process 100 frames. Okay, from those 100 frames, I need to identify while I'm doing page replacement which should be used. In that case, this reference bit would be, because not every frame would be used. So we would be good to know using this frame reference bit whether a frame is called or not. Replace any page with the reference bit equal to 0. So now it is much easier for us to look into the reference bit to replace the page. If there is a page available with reference bit 0, we don't care about anything. We just replace it and make the frame available. Do you agree with me? Is that simplistic method? Now, there is an algorithm which uses this policy and is called second chance algorithm. So what second chance algorithm is? So if the page is to be replaced has a reference bit equal to 0, it is replaced. If the reference bit is 1, then the page is given second chance. It is not being replaced. So what is done for that particular page? Reference bit is set to 0. Leave the page in the memory, and its arrival time is set to the correct time. This is the modification done for that bit. Let us suppose we go over looking into, because this is now going to be a sequential kind of search. So we look into each bit 0, 0, 1, 0, 1, 0, 1. So we wherever we find 0, it will be replaced. If we find 1, what we do is we make that reference bit 0 and move forward and give it a second chance and then move forward to other, this would be clear here. So how it is implemented? It is implemented using circular queue. So all of you know what is circular queue. So let us suppose we wanted to find that our next victim, but when it searches this particular location, the reference bit, it was 1. So if it is 1, it should be given this page should be given a second chance. So the pointer would move to here. Now again, this is 1. So again, this page should be given 1 chance. So this page and this page are given second chance. Okay, now this will be 0, this will be 0, and this is here. It will be moved. So this is how it is moving. So it is being set to 0, both the set to 0 and moved here. So whenever a reference bit found is 0, this page would be our new. Is it clear? So what I'm saying is, I'm saying that for each algorithm, for each frame, we keep a reference bit And that reference bit is used to identify whether this is referenced or not. If it is referenced, it will become 1. If it is not referenced, it will become 0 only, because it starts with 0. So now we have to find out the victim. With this algorithm is implemented based on the circular queue. So to find out the next victim, there is a circular queue. So in a circular queue, we know that there is a pointer. Because it's a circular queue, so we go one by one. We try to find out the victim frame. So we search here, search here, search here, search, and then we look for the victim frame. So let us suppose our pointer was here to find out the next victim. For that, this value was 1. This value was 1. So when it is reference bit is 1, it will be converted to 0, and the timer would be set to the current time. Then it moved to the second one here, because this has been given a second chance. This has been given a second chance. We make it 0, and second chance is given. Now it moved to next to look for the victim. So it is again 1. So in this case, what would happen? It will make this 0 and move to the next one. Now this is already 0. This frame and this frame has been given second chance, but this is already 0. So what can be done? This could be your new victim frame. So you can replace this frame. Now another algorithm, which is just an extension of it, rather than keeping 1 bit, we keep 8-bit byte for each. So 8 bits are used. So 8 bits are used for each page frame whenever they all are 0 first. So whenever a page is referenced, the most significant bit is made 1, and then it is shifted towards right. So every time when we are going to write anything, we shift to right and write into the most significant bit. And this would be read after some time. Like let us suppose after 10 iteration or 8 iteration, we are going to read this, and the value of this would tell us which one would be the, because for each page there would be this 8-bit long byte. So it's byte basically. So 8-bit register. So 8-bit register, if all are 1, so it means that within last 8 cycles, this has been used each time. So this value is higher than this value. Let us suppose one page with this value, and suppose this page, one page with this value. Which one has a lowest number of references? This is page B and this is page A. Which one has lowest number of references? B. So B become our next victim. This is another algorithm. This is another algorithm which has additional reference bits to identify the page frame. Then we have another second chance algorithm. Another second chance algorithm here, for each page, reference bit and modify bit is calculated. We looked at the pair. So this is the priority. This is having highest priority. This is having lowest priority. If both are 0, 0, then it is neither recently used nor modified. 0, 1, not recently used, but modified. This is modify bit. This is modify bit. This is reference bit. This is recently used, but clean. So this 1, 1 is recently used and also modified. Remember, we try that we should be giving a chance which is already if something is modified, we have to rewrite its content into the secondary storage. That will increase the swap out process. So if we can keep a modified page into the memory, that would be better, because there may be more modifications expected to that particular page. And if a page is not modified, the copy is already there, we can easily replace that particular thing. So this class, the 4 levels, are used to make the judgment which should be replaced. So based on if there are victim pages, we look into this class, and based on that, judgment made. Now another is the counting algorithms. So counting algorithms, they count the number of references. So rather than the method we have discussed, one is with extra bits. Now there may be the counters, special counters we initialize, that whenever there is a reference, the counter goes up. So for that, we have algorithm B is frequently used. So it means that we replace a page with smallest number of count, And then there is a most recently used algorithm. So most frequently used algorithm says that an frame which is most frequently used has a largest count size would be replaced. So this basically consider that the smallest count is probably the frame which is just brought in and has not been used yet. So there are different algorithms that can be used for page replacement. And now we are moving toward allocation of frames. So in allocation of frames, we can allocate the fixed, we can do the fixed number of allocations, or we can do some proportional allocation. So there should be at least minimum number of frames. Those are allocated to each process so as to give the performance. There are strategies. One is a fixed allocation strategy, and thus we find that if we have 100 frames and then we have 5 processes, then we can give 20 frame to each process. This is same for all, and all the processes are considered of equal priority. Then we have proportional allocation. Like there may be the processes which one may need 100 pages, one may need 1,000 pages. So we cannot allocate the same number of pages to each and every process. In that case, the proportional is done. So let us suppose the size of S1 is 10. The size means the number of pages. It requires 10 pages. It requires 127 pages. Okay. So now we have to allocate 64 frames. So in my memory, I have 64 frames. I want to allocate these to different processes, one with page 10 and other with page 127. So in that case, what we do is we perform the sum of all the pages. So 127 is equal to 137, and we do the proportion of it. So here 10 by 137 into 62, it becomes 4, and here it becomes 57. So process P1 would be allocated with 4 frames. Process P2 would be allocated 57 frames. So this is proportional allocation of frames. Then we can add priority also. So if there is priorities for different processes, then based on the priority, we create give a different allocation to the algorithms. There are two types of allocations, and one is global and local. For we will be talking about the global replacement. So the process select a replacement frame from the set of the frames, and what is global replacement here? So global replacement is basically, rather than just looking into replacing the pages which are allocated to one particular frame. Now we have done the allocation. So there are two types of allocation that can be done. So within the number of frames given to a one process, or within each frame, inter processes or intra processes. So we can say that one is, let us suppose we have process P1, process P2. So there are number of fixed frames which are given. Now, if there is a free frame request, so we can say the local replacement is, if this relates to P1, so the replacement should be done from within this local number of frames which are allocated to P1. This is one thing. This is P2, and global replacement is being used, then it can also replace the frame from P1 or P. So based on what replacement policy is being used, the frames would be made freed. So either from within the allocated quota of that process, or within all of the processes. The frame could be allocated from any process from the which is running. So process selects a replacement frame from a set of all frames. One process can take frame from another process. Whereas local replacement is, each process selects only its own set of allocated frame. I hope this is clear to you. Now, what is done? There is a maximum and minimum threshold. The free space is to be kept For that, let us suppose there is always a free frame list. So some proportion is always given to the free frame list. So the operating system would keep on checking the free memory from the RAM. If it goes down, then it will allocate, it will free some swap out few frames from the RAM to the secondary storage. So that is this minimum threshold. So the minimum value of the free space that should be kept is minimum threshold here, and the maximum threshold is whenever the minimum threshold is reached, the kernel would start allocating the free up the RAM and start performing the swap out. It keep on doing till the free memory become equal to or greater than the maximum threshold size. I hope this is clear. So minimum threshold is the minimum empty, the free space is to be kept. If it goes below that, let us suppose I want 10 MB of my RAM always free. My processes are running like that and it become 9 MB, the free space become 9 MB, the kernel would start the swap out process. So it will create the swap out processes, keep on doing till it reaches the maximum threshold. So let's suppose my maximum threshold is 15 MB. So it will keep on swapping the frames to the secondary storage till it reaches the maximum limit, maximum threshold. So this is done for global allocation, and this strategy is used to free up the space. So there are in Linux, there are out of memory killers. Those are used. Those killers basically replace the programs, terminate the processes, and how it is done. There is a score maintained for that. The high score, it increases. There is OMM score for each and every process, and which could be seen, and the highest score process would be deleted and terminated by OMM killer routine. So there is one killer routine which is running and creates an out of memory signal and tries to kill the processes or move the processes which are having the highest OMMs. So this can be seen in your Linux system. You go to proc directory, and for a given PID, you can see there is an OMM score for that particular process that we can witness. And this finishes your chapter 10, and the time is already up. So I will release the poll, and